Hello, everyone. My name is Ramses Brazal, and I'm the Chief Mechanical Engineer for Anteater Electric Racing at UC Irvine. Today, I'll introduce you to our very exciting project, Ampeater. Ampeater is an electric Formula-style race car that's been developed over the last 2 years by students on our team. It's been re-engineered to ensure that we can meet FSAE competition deadlines after long COVID-19 shutdowns. Our vehicle is powered by dual brushless DC motors in the rear that can output 240 Newton meters of torque combined under a 3-to-1 gear ratio configuration. The maximum motor speed reaches up to 3,600 RPM, and our max vehicle speed is 73 miles per hour. The accumulator assembly, which is our battery pack, is designed by our batteries team. It's configured with 26 lithium-ion cells in series and 24 in parallel, giving 5.6 kilowatt hours of energy and a pack voltage of 93.6 volts. Ampeater has a double wishbone type suspension with modular uprights to allow for changing suspension configurations and cost effectiveness. The suspension is designed to attain a 1.14 front and 1.36 rear motion ratio respectively, and our wheel and tire diameters are 13 and 20.5 inches. Ampeater features a 64-inch wheelbase, a 50-inch track width, 10.4-inch center of gravity, while weighing 600 pounds without the driver. This image shows Ampeater in development. We are currently working very diligently to get this vehicle ready for the Formula SAE competition. The Formula SAE event is a global competition that enables students to design, build, and test the performance of real vehicles. Furthermore, design judges from the automotive industry evaluate student teams on their ability to apply engineering skills in design, fabrication, analysis, testing, and presentation. This project provides my teammates and I the opportunity to develop our abilities in a very real engineering environment. Our goal is to develop each and every student with practical engineering skills, real world knowledge, and experience that would help them in their future careers.
Hello, my name is King Choi, and I'll be presenting for suspension. During the spring quarter, the suspension team began manufacturing Ampeater Evo. As we left off the winter quarter with the rolling chassis, we began organizing our goals for complete suspension system integration, also achieving 100% FSA rules compliance while competing in the FSA competition in the summer of 2021. Listed to the left are design parameters. In the beginning of the quarter, we implemented a test bench to measure the turn radius of our vehicle. We noticed that with the current parallel fixtures designed for Ampeater 1, this gave us a turn radius of 17.9 feet for a right-hand turn and 15.7 for a left-hand turn. These values did not meet the requirement of 14.76 feet, which is the tightest hairpin turn during the dynamic event of the competition. Therefore, after testing, we structured solutions to meet the turn requirement, leading to the design of our new steering fixtures. We have shown the finite element analysis done on the component with the sketch of the steering geometry designed in SOLIDWORKS, giving us a theoretical turn radius of 14.4 feet, improving our value to meet our requirements. Attached are pictures comparing the new fixtures to the old ones, as well as a dynamic model with the new steering fixtures. Once our new steering fixture arrived, we assembled and tested our new turning radius as right-hand turn of 13.5 feet and left-hand turn of 13.8 feet. These values exceeded our theoretical value and our minimum requirement. We continued our quarter calibrating our camber and toe, and shown to the right is our string alignment system, along with various processes to finish manufacturing. Because the design of our uprights are modular, we are able to adjust the camber using shims while all four wheels make contact to the floor. We adjusted our static camber to be set at -1 for both the front left and right, and -0.5 for the rear left and right. We verified our suspension system is compliant with FSA technical inspection and readiness for competition. This included verifying all fasteners maintain critical lock nuts and is symmetrical left and right. We ended our quarter with a fully integrated suspension, but our vehicle is still in preparation to compete in the Formula SAE this summer. Thank you.
Hello, everyone. My name is Mark Takahana, and I'll be presenting the accumulator subsystem. Our primary goal is to protect the operator, bystanders, and battery, achieve 100% FSAE rules compliance, and complete the endurance event. The accumulator relies on a 5.6 kilowatt-hour battery pack made up of cells with a nickel, manganese, cobalt, lithium-ion chemistry. To keep the pack at a safe temperature, we use 3 thermoelectric cooling modules that circulate cool air inside the container. To interface with the chassis, the accumulator container has 10 7075 aluminum mounts. In designing the battery, we picked modules that allowed voltage sensing of 100% of the cells and temperature sensing of 40% of the cells. We also have 3 means of overcurrent protection, 2 hardware and 1 software. These help us pursue safety and rules compliance. We also selected 2 max currents, one for endurance and another for acceleration. This gets at our goal of completing the endurance event. In the figures on the right, you can see the battery and its maintenance plugs. We arrived at the current values by modeling the vehicle dynamics in Simulink and putting that model through a drive cycle collected by our ICE team at their competition in 2019 during their endurance run. The aluminum container, which houses the battery and its supporting components, such as the battery management system and thermal management system, was designed for assembly with pre-cut holes in one of every 2 mating parts, such that there is a stencil. This can be seen in figure 9. This practice shaved off time and allowed construction of the internal frame to be completed within 4 4-hour sessions. Also, by relying on CNC cut parts for stenciling, we achieved our design dimensions to 60 mils. To save time and money on parts, manufacturing, and maintenance, we used 1/4-20 fasteners throughout the structure of the container. In figure 10, you can see the container ready to be integrated with a high voltage battery and electronics. To manage the temperature of the battery, we designed a battery thermal management system based on thermoelectric coolers, which turn a voltage gradient into a temperature gradient. In our case, we power the thermoelectric coolers, which cool the inside of the container and warm the outside of the container. Heat sinks and fans improve the convective coefficient of heat transfer both inside and outside the container. This technology has the benefit of being light, single phase, modular, and controllable. We tested our battery thermal management system on our container by placing water and a heating element that imitated the heat capacity and heat generation, respectively, of the battery. We discovered evidence that our battery should not require an active thermal management system during the most strenuous event, the 22-kilometer endurance event, provided that the starting temperature be under 46 degrees Celsius. This is to be confirmed with physical testing with the actual batteries. To join the container with the chassis, we designed a set of 10 mounts that connect the gusseted tabs on the chassis. We selected a simple geometry so that UCI students could machine the parts reliably, which they did. For quick mounting and dismounting, we also selected clevis pins with stronghold cotter pins. Now, last year, we were asked by competition judges for physical testing of our mounting system. In response, we got benchmark simulation data for our redesigned mounts for this year. The results for the simulation were satisfactory. So then we designed fixtures for our mounts out of mild steel. Our plan was to have an Instron machine subject these mounts to 15 kilonewtons in accordance with an FSAE rule in 3 directions representing left, right, forward, backward, and up, down forces. After manufacturing the fixtures, we conducted our tests and found the mount to be satisfactory in all directions. In other words, the mounts did not yield. It was only the clevis pins that experienced any permanent deformation. And that will do it for batteries.
Hello everyone, my name is James Bond and I will be going over the chassis subsystem for Ampeater Evo. The primary goal of the chassis subsystem is to design and manufacture a stable platform onto which we can integrate every other subsystem onto the vehicle. This is achieved by pulling dimensional requirements from each subsystem to generate mounting hardpoints, which are used as the base to design a 100% rules compliant FSAE chassis using 1080 steel. From there, our primary concern is the improvement to the vehicle's torsion rigidity and bending stiffness, the former of which is vital to preventing deformation of driver impact structures, subsystem mounting points, and improving suspension performance reliability. This is largely achieved by internal frames, as can be seen in figure 2, between the battery protection area and the rear powertrain assembly. However, in regards to all designs, driver safety is held foremost in any potential changes. Once design work is complete and all teams have signed off on their integration geometry, the team's primary work shifts to the accurate manufacturing and assembly of the chassis. Procedures were implemented for EVO to reduce the overall production time from 6 months to 2 months, while lowering general error tolerance to 1/8 inch and half of a degree from desired design specifications. This was achieved by using a pre-planned manufacturing procedure to generate accurate tube profiles by breaking down the car into separate segments, as can be seen in Figure 1 of the front bulkhead. From there, manufacturing jigs and templates were produced so we could have a step-by-step plan on how to manufacture every part of the vehicle before the first tube member was ever cut. As you can see from Figure 1, our team carries out these actions wearing the proper PPE to prevent injury to our team members, as safety and proper tool handling training is a mandatory part of our subsystem. Tubes are then processed and assembled in manufacturing jigs, where they can be fine-tuned, resulting in pre-assembled chassis portions able to be fully welded safely and accurately in a repeatable manner. All of our chassis parts are fabricated in-house, meaning we have to take into account any potential equipment or skill limitations when designing the chassis. This was all done to reduce overall vehicle costs and give us greater control over necessary adjustments. From there, the chassis is subjected to rigorous validation testing to establish data sets to compare with our simulated values. As you can see, our actual torsion rigidity performed at around 63% of its simulated counterpart, which came in just under our desired factor of safety threshold. Comparison of the physical testing and simulations results showed us the issue of note most notably occurred around the junction seen in Figure 3. The tube was then replaced with a newly designed structure to correct this issue to some degree, as can be seen in the table in column 3. Validation like this is key to understanding not only how to improve the current vehicle, but also future vehicles, by verifying the performance of certain design choices of the car, and to help refine our manufacturing process. This will conclude chassis.
Hi, I'm Diego Ganara, and I'm going to be presenting for Aerobody. So when it came to designing the body kit for Ampeater 2, we prioritized manufacturability and serviceability. These considerations were defined in light of the pandemic, which greatly limited our access to our manufacturing lab. Our design solution came in the form of minimizing the amount of parts with complex geometry. As a result, the body kit consists of 14 flat side panels, in addition to the nose cone part. Each of these parts are individually fastened to tabs which were welded onto the chassis. The segmentation of the flat body panels allows us easy access to specific portions of the cockpit for maintenance on components located inside. This design also makes us FSA compliant regarding driver safety from debris in the front and sides of the vehicle. The body panels, which were designed for easy manufacturing, were able to be cut on an Epilogue laser cutter located on campus. This design choice allowed us to allocate more time into the manufacturing of the aerodynamic front nose cone and top panel. Due to the three-dimensional geometry of the top panel and front nose cone, we needed to utilize male plugs to manufacture the parts. We started by designing the male plugs with materials and processes easily accessible to us in the pandemic. After designing the matrix composition of these molds, we began to assemble them, utilizing a composition of laser-cut plywood profiles and XPS foam, which were cut, sanded down to shape. These assemblies were then layered with a hard shell of Bondo to create a smooth finish, which then was coated in a coat of primer and then polished. The smoothness of these molds was critical for the hand lamination of the fiberglass, specifically in the removal of the part from the plug after the curing process. We also took this year to create a foundation for future aerodynamic package designs by designing an aero package for the vehicle, which included a front wing and a rear wing. Our design was focused on having a minimal impact on the drag of the vehicle. To design these aero components, we learned and utilized software such as ANSYS Fluent, which was then replaced by Siemens Star CCM Plus later in the year. Although we were unable to see our designs materialize into physical models, we ensured that these designs and the processes associated with them were served as a good foundation for future teams. And that's it for Aerobody.
Hello, my name is Juan Garcia, and I'm the Human Interface Manufacturing Lead. The design requirements of the steering system are to meet a 14.7-foot turn radius. The steering wheel must have less than 7 degrees of play, and the steering wheel must be no higher than the front row hoop. We have included a few images of the CAD software as well as the steering geometry found in Figure 3. The pedal's goal is to meet FCE requirements, withstand their maximum load case, and allow the driver to lock all 4 wheels under braking. We have implemented a 5.5-to-1 brake pedal ratio, which allows the driver to lock all 4 wheels with 129 pound force of pedal effort, which is acceptable. We have implemented an upright pedal geometry to minimize longitudinal space in the front bulkhead. We have also implemented 2 torsion springs for actuation of the accelerated pedal to improve serviceability. The brake system's service manual is a document that was created this year. The goal of the service manual is to generate a clear, thorough, and professional service manual to aid manufacturers, technicians, and design engineers in implementing, testing, and troubleshooting the vehicle's brake system. This document includes general advice, safety, and technical specification section, an implementation and integration section, and a troubleshooting section.
Hi, my name is Sean Winlow, and I'm part of the Human Interface subteam. This is our driver's control diagram, and it highlights all of the cockpit controls and signals the driver would interact with. These include LEDs, active switches, a voltage meter, a start button, an inertia switch, and an emergency switch. For our enclosures, the brake over travel switch enclosure and emergency enclosure were designed and manufactured. Most of our other enclosures were already manufactured from last year, but modifications needed to be made to some of them. More specifically, the accelerated position sensor enclosure and the master switch enclosure required major changes, which led to them being redesigned and 3D printed again. We also applied a protective coating on our enclosures to ensure that they were water resistant and to prepare them for the rain test.
Hello, my name is Timothy Young, and I'll be presenting the weld tabs for the 3D printed enclosures. Due to COVID, our electronic enclosures were originally mounted using zip ties as a quick fix. Weld tabs were manufactured and implemented as a more secure mounting method. The weld tabs themselves were cut from sheet metal using an angle grinder. The enclosures will be mounted with hex bolts and nuts for easy fastening and removal from the vehicle. A drill and soldering iron were used to create holes to allow for the enclosures and weld tabs to be fastened to each other. While designing and manufacturing, we encountered some issues along the way. We were not able to weld the master switch enclosure weld tabs where we originally anticipated because of the position of the accumulator container. Also, after consulting with the welder, we had to change the weld tab positions because he wasn't able to weld at certain angles. Our weld tab placement was designed around the circuit board to not interfere with it.
Hello, my name is Joseph Ciliato. I'm the powertrain lead here at Ampeater Electric Racing. For this year, we wanted to design a powertrain system around a set of dual electric motors that had been used in a previous Ampeater design. The idea would be to create or improve upon the existing design to create a more effective powertrain system that can be used in a later FSAE competition. The table on the left shows the specs for our proposed design of Ampeater, with a weight of 160 pounds, a gear ratio of 3:1, a proposed acceleration time for 75 meters of 4.7 seconds, while being controlled by dual Kelly controllers. In order to improve the powertrain system, we focused on designs for the chain guard and the motor control enclosure. For the control enclosure, we decided to redesign the removable lid to reduce water leakage, as shown in Figure 4. We also simplified the enclosure shape to make it more box-like, which would improve the manufacturability of the container enclosure, as well as improve the mounting points for the lid. For our chain guard design, we decided to avoid using a single component to cover the entire drivetrain, rather using two smaller components that would reduce weight and wasted space. As you can see in Figure 8, a more close-up view of the drivetrain layout in detail is shown in Figure 7. However, despite our design improvements, we were not able to manufacture these components due to COVID restrictions limiting our manufacturability options, and thus we decided to go forward with designing improving the existing Ampeater model to get it ready for competition in June. In order to accomplish this ultimate goal, we had to reassemble portions of the powertrain system that had been previously disassembled, as well as modify the control enclosure to achieve better controller packaging, as well as a higher standard of FSA rule compliance. In order to measure the power drawn by the controllers from the accumulator system, we designed an enclosure, as shown in figure 10 in blue, to hold the energy meter. Additionally, as shown in figure 11, we adjusted the controller mounting of the right controller in order to avoid interference with the left controller, which had been the case in a previous design. Finally, once the controller closures modifications were completed, a rain test was performed, which I'll go into the next slide. As mentioned in the previous slide, the control enclosure, as with any enclosure housing high voltage electronics, must be subject to the FSC rain tests, which means the controller enclosure needs to be 100% waterproof. As you can see in the video in figure 13, we sprayed the control enclosure from all sides for 3 minutes and then let it sit for an additional 2 minutes. Afterwards, we removed the lid and documented where water was found inside the controller enclosure. Through iterative testing with more and more insulation, we found after our final test that only a small trace of water was found, and through more sealant along the lid top plate interface, we hope that the control enclosure will be 100% waterproof.
This concludes the presentation for Ampeater at Ampeater Electric Racing. Thank you.